All right, next topic, kinetic energy and work energy theorem. This is out of chapter 5.2, section 2.2, or topic 5, which they like to call our book topics instead of chapters. All right, kinetic energy, it's energy of a moving object. And we learned yesterday that work was in units of joules. Energy in general, all energy is in unit of joules. So let's find define what the equation is for kinetic energy. Kinetic energy, which has a symbol of Ke, is equal to 1/2 times the mass of the object times the velocity of the object squared. So that is equal to a joule. And so let's kind of just figure that out. So if I have the mass times the velocity squared, so meters per second squared, so now I have meters squared over second squared. Well, what is that equal to? That's a kilogram meters second squared times a meter. This is a Newton and there's a meter. So this is equal to a joule. Okay. All right. So that is our units of kinetic energy, 1/2 mv squared. So continuing on, kinetic energy, symbol Ke. Trying to think. Actually, yeah, they actually have Ke on the green sheet. Let's go take a look on our green sheet, our equation sheet. Actually, they don't have Ke, they have K. So on our green sheet, on the equation sheet, which you will have, they have a symbol K. K equals 1/2 mv squared. Okay. So it's important to make sure that you are constantly referring to your equation sheet because you need to know where everything is and what it looks like. So K in their on their equation sheet is kinetic energy. I don't like that because K can also be Kelvin. Okay, that's why I like Ke. All right. M is the mass of the object in kilograms because we're in SI base units. V is the velocity in meters per second. So if it's in something else, you better convert it. All right, important. Kinetic energy is a scalar. Now, we learned yesterday that work is a scalar and work can be negative. However, kinetic energy can only be positive. So let's take a look at that. It's not because it's a scalar that's why it can only be positive. It's because we cannot have a negative mass. And even if velocity is a negative number, meaning it's moving to the left or whatever direction we define as negative, we square it. So it will always be positive. So therefore, kinetic energy can only be positive. So that is known. All right, next example. Let's do an example. We have a 2,000 kilogram car that's traveling at 27 meters per second. It locks the brakes. It locks the brakes and skids a total of 50 meters to a stop. So let's draw a picture. 27 meters per second, skids to a stop. So delta x equals 50 meters. And we have final velocity is equal to 0. A, determine the initial and final kinetic energy of the car. Okay, so we will have kinetic energy initial, which is equal to 1/2 mv initial squared. So we got to be careful of our subscripts. So that is equal to 1/2 times 2,000 kilograms times the initial velocity, 27 meters per second, square it, and we will find that to be 729,000 joules. Another way to write that is 729 kilojoules. Okay. Kinetic energy final is equal to 1/2 mv final squared, which is 1/2 times 2,000 kilograms times 0 squared, 0 joules. Oh, that was C. We forgot to do a free body diagram. Let's do a free body diagram. That was B. So what is happening to the car? We have force normal upwards. We have force of gravity, which is equal to mg, which is equal to its weight. It's traveling in this direction. And force of kinetic friction is to the left. Okay. How did I know that? Well, if it's coming, that's the only force that is stopping me. It's sliding, it's skidding. Okay. So I did B. I did, this was A actually. This was B. C. What type of force was doing the work on the car while sliding to a stop? Remember what work is? Work is equal to force times distance times cosine theta. Did force normal do any work? No, because theta is equal to 90 degrees between the force and the displacement. So if I'm traveling to the right, force normal is straight up, that's 90 degrees. Force of gravity is straight down, that's a 90-degree angle to the displacement. So theta is 90, cosine of 90 is 0. So there's only one force that can be doing work, and that is the force of friction. It's slowing the car down. Something has to slow it down. So when you speed something up or slow it up, speed something up or slow it down, you're actually doing work on the object. D. Oh, I knew that. I was trying to find. Okay, this is what I forgot to do. In A, they also asked me to find the change in kinetic energy. The definition of change in kinetic energy: anything changed, delta x, delta t, delta velocity. The change is the final minus the initial. Which is going to be equal to 0 minus 729 kilojoules. So the change in kinetic energy was equal to a negative 729 kilojoules, or 729,000 joules. D. What was the net work done on the car? Well, we just got finished finding out that work done by force normal, force of gravity was 0. So we have to add, there's 3 forces. So we have 3 forces that have the potential to do work. So we know the force of kinetic friction plus the work done by force normal plus the work done by force of gravity is equal to the net work. These 2 are 0. So I know that the only force that's doing work on the car is force of kinetic friction. Now I happen to know just by some things that the network is equal to negative 729 kilojoules, or 729,000 joules. Now, how did I know that? Well, it's what we're gonna learn on the next page. So if you don't believe me, let's determine the force done by kinetic friction. So first we gotta find the force of kinetic friction. So how do I find the force of kinetic friction? Well, I've got to sum the forces. I'm going to sum the forces in the x direction, which is equal to mass times acceleration in the x direction, which is equal to the negative force of kinetic friction. Do I know acceleration? No. Can I find acceleration? Sure can. I have 3 things. I know initial velocity, final velocity, I know delta x. So I can use kinematic equations and find that acceleration is equal to the final velocity squared, initial velocity squared, divided by 2 delta x, and that will equal a negative 7.29 meters per second squared. Okay, so then I can find force of kinetic friction by plugging in force of kinetic friction is equal to the mass of the car, kilograms, times negative 7.29 meters per second squared. And I will find the force of, those negatives are going to cancel. The magnitude of the force of kinetic friction will be 14,500 newtons. So let's go back to our work done by kinetic friction, and that is equal to 14,500 newtons times the displacement d, right? So that's 50 meters times, well, what's theta, cosine of theta? Well, if I'm traveling to the right and the force of kinetic friction is to the left. My angle is 180 and cosine of 180 is -1. So the work done by kinetic friction is, that works out to be 729,000 joules, which is equal to, you'll often see it in kilojoules. Notice it's equal to the change in kinetic energy, which brings me to the next topic. This is one of the most powerful theorems in our physics journey that we're going to take, the work energy theorem. It's actually not listed on the green sheet or your equation sheet like this, but this is what the work energy theorem states. The net work, the work done by all the forces added up, done on an object is equal to the change in the object's kinetic energy. And this holds true no matter what, forever and ever and ever, okay? And there's a flipping physics video that actually uses calculus to prove this. So the work net is equal to the change in kinetic energy. If you have a net force, which means you will have a net work on an object, you are going to have a change in velocity because you have acceleration, and it is equal to the change in kinetic energy that object experiences. Your equation sheet does not have this on there in this form. It looks like this. Energy is equal to work, which is equal to, hold on, let's go find it. Can't remember it off the top of my head. There it is. I knew change in energy is equal to work. What work? Net work. They didn't say that, okay? But it's implied. The change in energy is equal to the total work done on the object, okay? Not sure I like how they present that on your equation sheet, but this is how they present it on your equation sheet, okay? All right, now let's talk about a problem that we did yesterday, and let's use this to solve for some things. Recall from yesterday's lecture that we had a situation where a student put a horizontal force on of 3 newtons on a 1 kilogram box that was initially at rest, right? The velocity initial is 0. Delta X was 4 meters. Okay, yeah. We were given the kinetic friction coefficient between the floor and the box. We found the work that was done by the student to be 12 joules. We found the work that was done by the force of friction to be -10 joules. We knew that the force, and we calculated the force done on the box by force normal and force of gravity. They were both equal to 0 because cosine theta was 0 because we have 90 degrees. And we found the net work on the box to be a total of 2 joules. Now let's assume that I wanted to know the final velocity of the box after the student pushed on it for 4 meters. How would I have solved it before? We have the force applied, and we have the force of kinetic friction. Okay, we found yesterday that the force of kinetic friction was equal to, what do we find it to be? 2.5 newtons. Okay. So if I wanted to find the final velocity, I only have 2 variables. I have the initial velocity and the delta x. So I'm going to have to use Newton's second law to find acceleration, which would give me my third variable. So I can sum the forces in the x direction, which is mass times acceleration in the x direction. I have the force applied by the student, I believe it was a student, yeah, minus the force of kinetic friction. And I can solve for acceleration. I can find that acceleration in the x direction is Fa minus force of kinetic friction divided by the mass, which was 1. And that would equal, with all my numbers plugged in, find it. Where'd it go? Roses, never mind. Oh, there it is. There we go, I found it. 3 newtons minus 2.5 newtons divided by 1 kilogram, which is equal to 0.5 meters per second squared. Sorry for the delay. So now I know the acceleration. I'm still trying to find final velocity. This is a lot of work. Okay, so I know acceleration, I know I know initial velocity, I know the displacement. So how do I find final velocity? I find final velocity is equal to the square root of the initial velocity squared plus 2a delta x, which is equal to the initial velocity, which was 0, plus 2 times 0.5 times delta x, which was 4. And I will find the final velocity is equal to 2 meters per second. Okay. Now, that's a lot of work. Now read question E. What is the final velocity of the box after 4 meters? In the past, we would solve this problem using kinematics, which is what I just did. I used second law to find acceleration, and then I used kinematics to find the final velocity. We can now solve this problem using the work energy theorem. Here's how it goes. We know that the total work added on the object is equal to its change in kinetic energy. Well, we have found that the work done by the student was a positive 12 joules. The work done by the force of kinetic friction was a negative 10 joules. The work net is equal to 2 joules. Okay. We have just learned that the net work is equal to the change in kinetic energy. What is the equation for change in kinetic energy? Kinetic energy final minus kinetic energy initial. Let's continue. What is the equation for kinetic energy final? It's the mass times V final squared minus 1/2 mv initial squared. What was the initial velocity? 0. So we know that the net work in this situation, which we know to be 2 joules, is equal to 1/2 mv squared. Or v final squared, excuse me. What are we trying to find? Final velocity. Can I solve for final velocity? Sure I can. Final velocity squared is equal to 2 times the net work divided by mass. Take the square root of both. So I find it to be the square root of 2 times, what's the net work? 2 divided by the mass, which was 1 kilogram. Square root of 4 is equal to 2 meters per second. Heck of a lot easier to apply the work energy theorem to problems if you know the forces if you can figure out the change in kinetic energy or apply this theorem depending on what they give you. This is a much more robust approach to problems. That is the entire lecture for Friday. We're going to use the rest of the time to work on the lab. I've changed the date of the lab to a later date. So for those of you who are online, if you have troubles, you might want to reach out to me. Either I'll put something together or I'll Zoom you. Okay, have a great day. Hope this makes sense. Most important, kinetic energy equation, work energy theorem. The net work is equal to the change in kinetic energy. That's what I got.